Good morning, everyone. My name is Francesco Ambrogi, and I'm a PhD student at Queen's University in the Turbulence Simulation and Modeling Lab under the supervision of Professor Ugo Piomelli. Today, I will be talking about my research topic, which is a large-eddy simulation of a boundary layer with unsteady pressure gradient. So the motivation behind my research is basically what's in common between these two very different systems, a swimming shark and a pitching airfoil. In all these cases, the boundary layer very close to the surface is experiencing unsteady pressure gradients, which vary both in space and time. In the swimming shark case, for example, the fast-changing body curvature generates a cycle of alternating favorable and adverse pressure gradient. This might also lead to a transient separation process, which is often connected to the efficiency limit of many systems, dynamic stall, and in general to a drop of performances. So then why are we interested in simulating these cases? Well, first of all, there is a lack of data compared with what has been done using steady pressure gradient cases. We want to improve our way of designing flow control devices, but also by simulating these cases using LES and DNS, we can generate extensive data sets that can improve our modeling capabilities. So the main outcomes of my research are the fact that the oscillation frequency greatly affects the transient separation cycle. There is a limiting frequency below which the separation region is highly unstable. And we also found very strong dynamic hysteresis effects caused by the unsteady pressure gradient. The numerical methodology I followed was solving the filtered Navier-Stokes equations, where here overline denotes the filtering operator. The subfilter scale stress tensor tau ij has been modeled using the Vreeman eddy viscosity model. And regarding domain and boundary conditions, I am simulating the specially developing turbulent boundary layer in a very long domain in which the inflow condition is taken from an auxiliary parallel simulation and rescaled in the inflow of the actual simulation using the land method. And the top boundary condition prescribes the vertical velocity profile in order to generate the pressure gradient on the bottom. The U infinity, the streamwise component, is then given by applying a zero vorticity condition at the top. All the simulations that I performed are wall-resolved simulations. I used a second-order accurate finite difference code on a staggered grid, and here you can find the grid size in wall units. I also performed a grid convergence study to validate the present resolution. Here you can see U infinity and V infinity in the domain, and the unsteadiness is generated by the profile of V infinity in the domain, which has a steady component chosen to match previous APG, FPG simulation, and a dynamic oscillation component where the most important parameter is the reduced frequency K, which represents the ratio between the convective timescale of the flow over the imposed unsteady timescale. LPG here is the length over which the pressure gradient varies, and U0 is the streamwise free stream velocity at the inflow plane. The boundary layer then will go from a zero pressure gradient at phase zero to a region in which a favorable pressure gradient is followed by an APG, and then back to a zero pressure gradient again, to then go to a region where a strong APG is followed by an FPG, and then back to zero pressure gradient again until the cycle repeats itself. We performed simulation for a wide range of reduced frequencies, then 1 and 0.2, in order to have a wide range of physics. The oscillation period has been divided into 20 equally spaced phases in order for us to carry out phase averaging for every quantity. And we also performed 5 steady simulations for comparison between steady and dynamic simulation. The first result that I would like to show is the phase average streamwise velocity contours. As the animation plays, I would like to focus your attention in two regions in the domain. First, the center of the domain, where separation takes place. We can clearly see that we have the formation of a closed separation bubble for every case, though the size of the separation region greatly changes as we decrease the reduced frequency. The other region of importance is the downstream region for the k=1 case. We can clearly see that the separation region is highly unstable and is advected downstream and periodically washed out of the domain, behavior that has been observed over a backward-facing step. Now, if we freeze the moment when we reach the maximum adverse pressure gradient phase at phi 270, we can actually compare the size of the 3 separation bubbles for the dynamic cases with the corresponding steady case. And we can clearly see, for example, when the frequency is high enough, 10 and 1, separation bubble doesn't have the time to grow as thick as in the corresponding steady case. However, interestingly enough, the length of the separation region for the K10 case is comparable with all the other cases, but for the K equal 1 case, the length of the separation region greatly decreased under the effect of the unsteady pressure gradient. When we decrease the reduced frequency down to 0.2, we can clearly see that we are approaching a quasi-steady state. And now the dimensions of the separation bubble, both height and length, match very well the steady calculation. If we take this analysis further and we analyze velocity profiles at 3 different streamwise locations before, at the center, and after the separation bubble for 4 phases in the cycle, we can clearly see that in the favorable pressure gradient region, profiles match reasonably well the steady calculations, the black dots. But great differences arise when separation takes place. This is, of course, because of the size of the separation bubble, but also, even though the 0.2 case is going towards a quasi-steady state, it is characterized by quite a stronger backflow in the center of the domain. The most interesting case, though, is these two phases, because at these phases, the boundary layer is experiencing the same pressure gradient. The only difference is at phase 0, the flow is going towards the accelerating side, and at phase 180 degree is coming from the acceleration side and going towards separation. We can clearly see that there are differences, especially for the K equal 1 case, which tells us that there are hysteresis effects. In fact, by dividing the cycle in 20 equally spaced phases, this gives us 9 matching phases in which the boundary layer is experiencing the same pressure gradient twice in a cycle. We can divide them in 3 groups. We have the separation side containing all the phases when U infinity is less than 1, the 2 matching phases when U infinity is 1, 0 pressure gradient, and all the matching phases when U infinity is greater than 1, the acceleration side. Now, dynamic hysteresis is observed when a physical quantity assumes 2 different values at corresponding phases in a periodic cycle. Therefore, by evaluating the difference between all these matching phases, we can actually map the dynamic hysteresis in the domain. If this quantity is 0, there is no hysteresis whatsoever. If it's significant, there are very strong hysteresis effects. Now, if we do this analysis for the K10 case, the high frequency, we can clearly see that there is almost no hysteresis whatsoever in the domain, nor in the separation side, the blue region, nor in the acceleration side, the red region. If there is very close to the wall and less than 5%. Doing the same for the 0.2 case, though, tells us that there are indeed very strong hysteresis effects in the separation region. This deep green region tells us that the flow coming from the acceleration side is actually much faster than the flow going towards it. This difference at the free stream, remember, we are fixing the V infinity, therefore U infinity adapts itself by mass conservation, therefore it lags behind the V infinity. Now, these effects are smudged towards the 0 pressure gradient phases and then almost absent in the acceleration side. However, doing the same analysis for the K1 case not only tells us that the hysteresis effects are present throughout the whole cycle, but they are steady in space and they grow in magnitude in the separation side, and due to the advection of the turbulent structure, they are pushed towards the outflow in the acceleration side. Not only that, but this alternating color, green and purple, tells us that there is a great spatial decorrelation which translates into a phase shift. This is very easy to visualize if we pick 2 different locations downstream the separation bubble for the case K1 frequency, and we visualize the velocity profile. We can clearly see that as in one location, the velocity profile decreases, in the other, the velocity increases under the effect of the unsteady pressure gradient. So to conclude, we performed simulations for a wide range of reduced frequency. The oscillation frequency greatly affects the transient separation cycle, and there is a limiting frequency between 10 and 1, below which the separation region is highly unstable. We also found very strong dynamic hysteresis effects caused by the unsteady pressure gradient. Now, my future plan is, of course, to quantify the phase shift and spatial decorrelation observed. I would like to look at higher order statistics and answer 2 main questions. How is the reduced frequency affecting the turbulent kinetic energy and Reynolds stresses? And what is the effect of this periodic washing out behavior on turbulence intensities? And lastly, what is the effect of the unsteady pressure gradient on turbulent structures? Well, thank you so much for your attention. That's all for me. Thank you.